Hello everyone, welcome back to Bytes of CSE. So in this lecture, we are going to talk about one of the simplest and most common classifiers available in machine learning, whose performance competes with quite complex classifiers in the literature. So we are talking about k-nearest neighbor. So in order to keep the length of the video within some reasonable limit, I have split the lecture into three parts. So this is the first part, which talks about the introduction to algorithm with some illustrative examples, advantages and disadvantages, and when to use this algorithm. Now k-nearest neighbor also has a regressor variant. Now let's move on to the algorithm part of it. So this is the basic KNN algorithm, and this is the algorithm for the classifier, but the regressor isn't very different from this. So the core part of the algorithm now depends on measuring the distance, a similarity between the train samples and the test sample on which the prediction is to be made. So suppose we have taken some data points, and they are of three classes, that is blue, yellow and purple. Now let's learn in very simple words how this algorithm works. So let's take a test data point, which is denoted as this cross mark. So what we do here is we compute the distance between this test data point with all the data points available in the data set, and then we sort the distances in ascending order, that is from lowest to highest, and we will consider the first k of that list. So what is a k? K is an integer, and what does k denote? K is the number of neighbors or the number of nearest points we are going to consider in order to determine the class of the new test data point. So the majority of that k points, that is the class which is the majority among those k data points, will be assigned to this new or the test data point. So let's look into the algorithm, which says that as input we'll be taking the training samples. So D, this is a big D, which denotes a set of the training samples, a test sample which is denoted by small d, and k. K is how many neighbors or how many nearest points are to be considered for the final decision. This is always going to be an integer. And in case of classification, we generally go for an odd number so that if there is a tie, it can be easily resolved. So in case of binary, of course, it's easier, but if there are a multi-class, so if we are going to take three neighbors and three neighbors belong to three different classes, that's going to be a bit difficult. So in that case, we'll be considering 4. So it depends on the value of your k. You will, the number of classes in your data set, you will consider this value k. So you have to be intuitive while considering k. So now we will compute the distance between this small d, that is the test sample, and every sample in the training set. Then we will choose the k samples in D that are nearest to the small d, that is the test point, and we denote that set by P. Then we assign D the class that is most frequent class or the majority class in that set, which is P. So when we are using a regressor, it's very similar. So for that new data point or that test point, we are going to be again considering the distance between this and all the data points in the training set. We are going to be sorting the distance, and we are considering the k nearest neighbors. And in this case, instead of using the most frequent class or the most frequent value, we are going to average the value. We are going to be considering the sum of the values, and we are going to divide that with this value k. Okay, and that is going to be assigned to this new data point. So if in any case you are considering only one neighbor in case of a regression, so whatever value, whatever target that neighbor has is going to be assigned to this new data point, and we are going to see that in a while. So we are going to consider an illustrative example for the classifier. So we have taken 3 training samples, and each of the training samples have 3 features, x1, x2 and x3, and this is the target variable, which is the class. What happened here? Okay, this is a class, and we are also given a test sample whose x1, x2, x3 values are known, and we are to assign the class of that test sample. So let's find the distance. Now here we will be considering Euclidean distance in order to measure the distance between the test sample and the other samples. Since this Euclidean distance is used by default in your scikit-learn, it's one of the simplest and most common distance measured used in KNN. So this is the formula for Euclidean distance. So for 2 points P and Q, the distance between them is we take the distance between the corresponding data points, that is, say x1 of training sample and x1 of test sample, like that. We take the distance, take the difference, we square them, and similarly for all the feature points we do the same thing. We add them up and then we take a square root. In simple words, let me say that. Say for measuring the distance between your test sample and training sample 1. So it will be x1 of test sample minus x1 of training sample 1, which is 4 minus 5 whole square plus 4 minus 4 whole square, and then 3, or rather 2 minus 3 whole square, and then we are going to take a square root like this. So 4 minus 5 square plus 4 minus 4 square plus 2 minus 3 square, which is, and after taking a square root it becomes 1.4. Similarly for training sample 2 it will be 4 minus 1 whole square, 4 minus 2 whole square and 2 minus 2 whole square, which is finally going to be, after taking a square root, 3.6, and for the last sample it's going to be 3.7. Now when we rank, or when we consider the distance, and when we are giving a rank to each of the test sample, so the nearest point is this training sample 1, then comes the training sample 2, and then comes training sample 3. So if we consider just one neighbor, this is going to be the class, that is 1. Test sample will be assigned a class 1. Now if you consider this training sample 2 and 3, both are more than twice the distance between this test sample and the training sample 1. So clearly training test sample has this class 1, or the class to be assigned is 1. Sorry, I just wrote it somewhere else. Anyways, but if you consider 3 training samples, if your value of k is 3, then going by majority, this class will be assigned as 2, and that will be an error. Because see, the number of training samples for your class 1 was less, or rather 50% of that of the number of training samples in class 2. So here comes one problem with k nearest neighbor, that if all data points in the training set are chosen as neighbor, then the majority class gets assigned to the new data point always, even if it is wrong. So in case of an imbalanced data set, it might be tricky to use k nearest neighbor, or you have to do some sort of a pre-processing in order to use k nearest neighbor, or you just have to be very intuitive or very careful about choosing the value of k. Now we'll move on to the k nearest neighbor regressor. In this case, I'm not going to go through like those distance and illustrative examples and all. I have directly used scikit-learn, and I'll just show you the whatever that I have uncovered. So for this, I have used just one feature, that is the value of x is going to be just 1. So there's just one x1. So, and the target is going to be, say it has feature 0 and the target is 0.1. For point x2, the feature gets the value of 1 and this is the target. So these are all random things. I haven't really used any formula. It's just very random. For feature point x3, there's just 1 and 3 and 1.7. So like that. And this is your XR, which is the feature, and YR is the target. And now from sklearn.neighbors, I have imported k neighbors regressor as KNR. So when we consider, we are first of all considering with the number of neighbors, that is your k value in this case will be equals to 1. And I have just fitted this data, this whole data set along with their target values. And now I have chosen one data point, say 1.5, say the feature value is 1.5, and I am about to see that what it predicts. So it went with this value, that is the x2 value. Now here's the interesting part. Up to just before 1.6, it gets assigned to x2, and when the feature value is 1.6, it gets assigned to x3. That is, it gets a target value as 1. Now in this case, I have considered 2, 3 and 4 neighbors for this point 1.5. When we are considering 2 neighbors, it's very easy because it considers both x2 and x3. These are the nearest neighbors for the data point 1.5. And what happens here is, it is, see, 1 plus 0.7 divided by 2, that is 1.7 divided by 2, which is 0.85, and you get this value as 0.85 when we are trying to predict the value for this. When we consider 3 neighbors, in this case the nearest point, this 1.5, will be nearest to 0, 1 and 2. And in this case, these 3 values will be considered and the average will be taken, that is 0.1 plus 0.7 plus 1, which is 1.8 divided by 3, which is array 0.6. This is your target value. And when we consider all the 4 neighbors, well, there is no choosing, all the 4 will be considered, and we'll take the average of all 4 of them, that is 1.7 plus 1 plus 0.7 plus 0.1, and what we get here is 0.0875. So you can just take a screenshot and you can just do it in your free time. Just find out if this is right, or whatever I'm saying, if that is right. Okay. Now there is one reason why I will not use k neighbors regressor, and this is the reason why. Now this is strictly distance based. Now here the maximum value for the feature was 3. Now when I try to find out the prediction for the feature which has a value 5, it outputs 1.7 because that's the nearest point. Now again, when I consider this value 7, Like this feature value is 7, which is more than twice of this feature value. It again gets a value of 1.7. The problem is there is no underlying formula that we are using. Like in your linear regression, or I don't have any linear regression video yet, but you have gone through MLP and all, I'm sure. So I have talked about this formula. This is a linear formula, Wx plus B. So this is a weight, this is a bias, and this is your feature point. So we actually work out some weight value, some bias value, and based on that, we output some result. In case of linear, of course, I'm not considering the non-linear case just right now. So if we would have considered something like this would have been a completely different story. This wouldn't have been the output. And of course, it should not be the output. Just because this is the furthest data point that is present, even some data point which is more than twice the distance away from this point be presented to the algorithm, it will output this value. So if I do not know that the test point belongs somewhere between the training distribution, I will not use k-neighbors regressor. So that's it. Now quickly let's find out the characteristics of KNN. Now this is very simple, very efficient, and also effective algorithm. I'm going to show you in the last part why I'm saying that this is quite an effective algorithm. It's surprisingly effective, in fact, for solving real-life classification with reasonable accuracy and, in fact, pretty high accuracy, more than 90% accuracy. And that's very interesting. The second part is it is one of the laziest learning methods. So it basically does not learn anything. It just ingests those training samples, and based on the distance, it gives you a class or a value. So it waits till the test data is produced, and so no learning model is created. And as I have said just in the regressor case, first of all, it makes no assumptions on the underlying data distribution. And number two is, it does not formulate any function to map the input to output. And this is also the reason why KNN is also known as a non-parametric algorithm. This is for these two reasons. Just note it down, because you might get asked in your interview why KNN is known as a non-parametric algorithm. Now, if we look into the disadvantage or the challenges of KNN, what we find here is, number one, it is pretty slow because you have to compute the distance between all the data points. So the complexity increases as the number of training data points increase or the dimensions increase. So the speed issue is somewhat tackled by divide and conquer algorithm, but still for very large data set, it is pretty slow. Then another is choosing the best k value. This is a tricky part, and this k value determines a lot. And in the next lecture, I'm going to talk about how this k value changes everything and how to determine the best k value. It's pretty a trial and error thing, but still okay. That is how the practice is, to choose the best k. Then also to choose the best distance or similarity measure, though in most of the cases Euclidean works pretty good. But sometimes in case your data set is a little not a very conventional one, and you are going to try to use KNN, it might be a little tricky. Euclidean might not work well. And then the memory requirement is pretty high because we are going to store all the training samples, and that means ONM space complexity, where N is the number of examples and M is the number of features. And similarly for computational cost, the computational cost is also like O(n)m time complexity. And we are actually measuring the distance between each test sample and all the training samples. So that is pretty high computational cost incurred here, and the time constraint we have already talked about. Now, when to and when not to use KNN. It's very easy to use, but if your training set is pretty small with less features, then you might use it. Or when the distribution, well, you don't know anything about the distribution, the data distribution, then it is also good to use, because like no assumptions are being made on the underlying data distribution, and the parameters are determined by the size of the training data set. So it just computes the distance between the data set and the test set, right? Like the training set and the test point. And when do we not use KNN? First of all, when the data set is very large or very sparse, and when the data set is pretty high dimensional. That is, if the dimension or number of features in your data is more than 100, it is advisable not to use KNN. It's safer not to use KNN. So that is all for today. And we are going to talk about how this K value changes everything in KNN in the next lecture. So stay tuned, and thank you for watching. Have a good day.